Alright, so in this example we have a collar O, which has a constant acceleration of a to the left, and a thin homogeneous bar of length L and mass m, which is pinned to the collar. We're asked to find in this problem a value for a such that the bar is held constant at an angle of theta. So because we're looking for an acceleration in this problem, we know we're going to need to start by drawing a free body diagram, and we're going to want to apply Newton's second law. And so if I draw a free body diagram for just the bar, we know we're going to have reactions at the pin joint at the top, given by OX and OY. We'll have a weight acting down, given by mg, and we know that this bar will have a tendency to translate with some magx in both the x and y directions, and we'll set those values eventually based on the problem specifics, and it'll have a tendency to rotate with some ig alpha. So with this free body diagram in hand, we can proceed on to the kinetics of the problem, and so we can start by summing forces in the x and setting that equal to mass times acceleration of g in the x. And if I do so, I'll have here that OX is equal to m times AGX. Let's go ahead and call that equation 1. I can likewise sum forces in the y direction here, set that equal to m times AGY. And if I do that, I'll have that OY minus mg is going to equal m times AGY. And we can call that equation 2. I can also sum moments. In this case, I'd want to sum moments about the center of mass and set that equal to I about g times alpha. And if I do that, noting that this interior angle here is the angle theta, I'm going to have a negative moment from OX, and its moment arm length in this case is going to be L over 2 times the cosine of the angle theta. And I'll also have a negative moment created by OY, and its moment arm will be L over 2 times the sine of the angle theta. And that's going to equal I about g times alpha, and we can call that equation 3. Now if we look carefully at these three equations, what we realize is that we have 1, 2, 3, 4, and 5 unknowns. And so we're going to need to develop some additional equations here to help us out. In this problem, those additional equations are going to come from the kinematics specific to this particular problem. In this problem, we're asked to find the critical value A such that the bar translates with the same acceleration essentially throughout. What this means is that we want the acceleration of point g in the x direction to simply be minus a. If it was any different value, then the bar would not maintain the configuration we were asked for in the problem. We can call this equation equation 4. Likewise, I need that AGY is equal to alpha is equal to 0, and we can call this equation 5 if you'd like. And this is important again so that we can maintain that constant value of theta we're asked for in this problem. Now if we take these kinematic variables and we plug them back into our equations up above, what do we get? Well, from equation 1, we get that the reaction OX should be equal to minus MA. From equation 2, we get that OY should equal mg. And if I take both of these facts and plug them into equation 3, along with the fact that alpha is equal to 0, I'm going to get that MA times L over 2 times the cosine of the angle theta minus mg times L over 2 times the sine of the angle theta should equal 0. Now if I look somewhat carefully at this equation, we realize here that we have some common terms, so we can factor out a m, and we can also factor out a L over 2. So I can rewrite this as saying that a times the cosine of the angle theta has to equal g times the sine of the angle theta. Or, perhaps written in a slightly more compact form, that the critical acceleration needed to maintain the bar at a configuration of theta is given by g times the tangent of the angle theta. So interestingly enough, this critical acceleration is independent of the mass of the bar, its length, etc., and it really only depends on the gravitational constant and the angle you want to maintain the bar at. This is very useful when designing things like gantry cranes, etc., where critical angles like this can mean the difference between a good placement and bad placement. Alright everyone, I'll leave it up to you to plug in the numbers at this juncture. I know you got it. Best of luck.